In this video, we're going to go over the interactive periodic trends activity. This Excel sheet does not quite properly work when it opens in your laptop. And so I have Excel on my desktop, and so we'll use this to go through. So you'll answer the questions as I am clicking. So question number 1 asks us to click on the atomic radius. And question 1A, atomic radius is the distance from the center of the nucleus to the outermost occupied energy level. What units are used to measure the atomic radius? And so here you have over on the left-hand side, you have the atomic radius, and then it says PMs. Those are picometers for the atomic radius. So picometers for the atomic radius. And then look at the big picture in general. What happens to the atomic radius as the atomic number increases? So what I'd like you to see is there is a spike once we hit the alkali earth metal, and then we go through the row, it decreases. So across a row from the alkali earth metal, element number 3 to element number 10, going across a row, the atomic radius decreases. Then we get a spike again, beginning with the alkali earth metal, and then going across the row, it decreases. Then we get a spike again at the alkali earth metal, and then this one involves more elements because you're moving across the D sublevel, but it decreases. So each section here, each one of these little sections is actually a row on the periodic table. High point for the alkali metals, and then decreasing across a row. Then question number 2 asks, just below the bottom of the graph is a pull-down menu that allows you to select the period of the periodic table that you want to see alone. And then so we can click here, and it says select period 3 only, and then click OK. Is there a trend within this period for the atomic radius? Well, yes, there is a trend moving across a row of the periodic table. Remember, a period is the same thing as a row, and the trend is that the atomic radius gets smaller as we move across a row. Is this what you expected? Why or why not? Remember, every time we move from one element to the next, we are putting more protons and more electrons into that atom. So as you move across a row, the atom squeezes in on itself because of that positive and negative attraction. Question number 3 asks to look at row number 4 only, and do you see the same trend? Yes, we do see the same trend. We see a little anomaly here, and there's a reason for that we'll talk about in another video. It has to do with the d orbitals and filling up the d orbitals. Then question number 4 on your interactive, fill in the blanks about the atomic radius. Atomic radius increases as you move down a family. As we move down a family, the atomic radius increases, and it decreases as you move across a row. That's question number 4. Question number 5 asks us to reset the pull-down menu to graph all the elements. So I'm going to click here, and then I'm going to select all of those and click OK. And now click on the side option called first ionization energy. So over here we want to plot the first ionization energy. This will graph the amount of energy required to remove the outermost electron from an atom. Look at the big picture. Is there a trend that you see as atomic radius, as atomic number increases? Here you start with the alkali metals, and in general it spikes up, then it drops, then it spikes up, then it drops, then it spikes up again, then it drops. So we see this pattern as you move from the left side of the periodic table, the alkali metals, to the noble gases, it increasing, and then it drops again, and then it increases, then it drops again. Now within each of these patterns you see slight anomalies where it pops up, then back down, then pops up, then back down. We'll talk in the next video about why that is. But overall, looking at that big picture, you're seeing a spike and then a drop as you move across a row, so a low value to a high value. Then when you start a new row, you start with the low value and go to a high value. How does this trend, letter number 5B, how does this trend compare to that of the atomic radius? Well, it's the opposite of atomic radius. If I go back here and click on atomic radius, you would start up high and then go down low. And first ionization energy starts low and goes up high. Does this make sense? We talked about in a previous video that the bigger the atom is, the easier it is to take an electron away. So a high atomic radius would be a low ionization energy. Or an atom that's a small atom that's holding on tightly to its electrons, small in atomic radius, will be difficult to remove an electron. So yes, these trends do make sense. They're opposites of each other. If I go to question number 6, pull down menu and select only 3. So if I only select 3, then we can see that trend where we start with the alkali metal and we go over to the noble gases. It becomes more and more difficult as you go across a row to remove an electron. And that is what we expect. In question number 7, we reset the pull down menu and now we click on electronegativity. So I select all of these. And then we go to electronegativity. There we go, electronegativity. So we see this pattern. Looking at the big picture, do you see a pattern? Yes, we start down low for the alkali metals and going across a row to the noble gases, we increase. Then we drop down again and then we increase to the noble gas. Then we drop down again and then we increase to the noble gas. How does this trend compare to the atomic radius? Well, let's go back and look at the atomic radius. It looks like the opposite of atomic radius. How does it compare to the first ionization energy? It looks very similar to the first ionization energy. Question number 8, now click on the tab at the bottom of the screen called Ion Properties. So down here we have Ion Properties. The graph shows the size of the period 3 elements. So across row number 3, here's the size of the period 3 elements. We start with a larger atom, and as we move across a row, the atoms get smaller because you're putting more protons and more electrons in, so it squeezes in on itself. In the top right corner, click the box that says Add Cations. So if we add the cations in, now you can see the cations are all smaller than the atoms. Why are they all smaller? Because when those atoms are losing electrons, they also lose the outer energy level, so it becomes a smaller atom. Notice Na in column 1A becomes an Na with a 1 plus. Mg in column 2A becomes a 2 plus. Al becomes a 3 plus. And then we really haven't talked about the 4th or the 5th column, so we could just look at these 3. But all 3 of these become smaller because they're losing their outer electrons. And by doing that, they're emptying their outer energy level. And because of that, it gets smaller. How does the size of the cation relate to the size of the original atom? Well, they get smaller. Now we add anions by clicking the box in the upper right-hand corner. Add the anions. And let's look to see if we can add in, there we go. So we're looking at phosphorus that becomes a 3 minus, sulfur that becomes a 2 minus, chlorine becoming a 1 minus. When we look at these 3, the anions get bigger. Well, why do they get bigger? Not because they gained an energy level or a principal quantum number, but those electrons come into the final energy level and it gets a little bit bigger because you've added electrons into that same energy level. Those electrons do not like each other, so they try to move away from each other, and it expands that orbital, expands expands that energy level. It expands that principal quantum number because you've added electrons in. Here you've added 3 electrons in. Here you've added 2. Here you've added 1. So now there's more electrons in that same area of space, so they spread out. They want to get away from each other. It's like if you were sitting on the grass with friends having a picnic and other friends came to join you, you'd spread out to give yourself space on that grass. Well, that's what electrons do. And so how does the size of the anions compare to the original atoms for the anions? The anions are bigger than the original atoms because of the added electrons and that same charge repelling each other, so they want to spread out. I hope this helps with being able to get the interactive periodic trends activity completed.